Welcome, welcome to part number 8 of module 6 on traffic assignment. And in this part, we are going to talk about equilibrium method. Okay, let's see if this thing is working. So, route choice behavior. What exactly is a choice? If you look at our 4-step planning process, if you look at step 1, which is trip generation is nothing but a choice of making a trip, the time of day, the purpose, and all. It is a choice. That's a user's choice. Second is trip distribution. That is also a choice about where that trip is destined to. In most cases, origin is home, and therefore, so in a vast majority of the cases, origin is fixed at home. But the destination, people have a choice. For instance, shopping, whether they go to Fair Oaks Mall versus Tyson's Mall. Work-wise, typically they don't change work that often, but shopping is more flexible. The third one is about mode choice. The word choice exists in mode choice itself, so that is also a choice. And the fourth one we are talking about is traffic assignment. That also depends on the route choice and the behavior associated with route choice. Now, we talked about all or nothing, stochastic, incremental, iterative, all these methods. So one thing that is important in all these methods is a robust path finding algorithm, shortest path algorithm, right? So now the question is the route choice behavior is going to stick to the shortest path from origin to destination? Or another way to ask this similar question is, if I know the shortest path between here and origin to destination is this, am I going to stick there? Is it going to be, am I going to stick to that choice irrespective of what other people are doing? So, in other words, here the question is your choice dependent on others' choice as well? So, the answer is yes, it is dependent, because as the volume increases, travel time increases. So we have seen that relationship, and it will play into our choice. So it's very important that we take into consideration into route choice. So equilibrium assignment is the most used these days in travel demand modeling software. And all methods you studied earlier, they were at some point they were used. Especially iterative assignment is still used, but not as much as even 15 years ago, thanks to the advances in computing. It's not necessarily the software, it's mostly the processing speed has increased, and therefore people can afford to adopt equilibrium assignment. We'll get to that later. The premise of equilibrium assignment is the network travel times, the link travel times are going to be so adjusted by people choosing their own paths in such a way that network will be in a state of equilibrium. What it means is that there is no incentive for people to switch their route. Keep in mind there is a distinction between a link and route. Route consists of a number of links. Link is one individual segment between two intersections. So a bunch of links make up a route. So we are talking about switching a route, not just one link, entire route from origin to destination. Keep that in mind. So when we say, when I illustrate with example here, when I use a route, treat it as a route. That means it can contain a number of links. So there are a couple of theories. One is user equilibrium and the other is system optimal. In user equilibrium, if there are multiple routes that are being in play for a motorist going from origin O to destination D, let's just say 3 routes. By switching from 1 to 3 or 1 to 2, he's not going to improve the travel time. Improve is the operative word, meaning it will not be reduced. At best, it can be equal if you switch. System optimal, on the other hand, it's a formulation that seeks to minimize the total system travel time. In other words, I go from my home to George Mason and you go from your home to a shopping. Regardless of your purpose, whatever it is, the entire network, wherever you do, so our combined choices are going to affect the system in such a way the total travel, the number of vehicle trips times the number of miles traveled by all of us is going to be absolute minimum. It's a theory. That brings us to Wardrop criteria. This Wardrop criteria is very famous. These criteria lead to the development of user equilibrium assignment method. The first principle says that journey times in all routes, I probably keep using that interchangeably. They actually, if they are in play, that means if they are being used, so the travel time on the ones that are used is going to be equal to or less than the ones that are not being used. So the keyword is used versus unused. So keep that in mind. And the second principle states, at equilibrium, the average journey time is the minimum. So average journey time of all travelers is. These two principles form the basis for equilibrium assignment. As I mentioned just a little while ago, there are two methods of equilibrium assignment. First is the user equilibrium and second is the system optimal. Let's talk about user equilibrium. This is based on Wardrop criteria, which we just talked about. And the two main assumptions in play here are travelers are going to make travel time decisions between any given OD pair entirely based on travel time. And the travelers a priori, meaning ahead of time, they know exactly what is going to be the travel time between point A and point B. Considering this method was developed decades ago, that assumption is a stretch. In today's world, you can probably envision a scenario where your travel time is chalked out because of lots of trip planning services that are available to you in RICS, even Google Navigation. They give you approximate travel time. But consider this like some 30 years ago. It is not possible to have prior information about travel time from any two sets of points. So essentially this all comes down to this. If two routes are used, their travel time is going to be equal. If there are 3 routes, 2 of them are used and 1 is not used, the one that is not used, unused one, will have either equal travel time to the ones that are used or more. So if you have travel time on route 1, T1, T2 and T3, 3 travel times, if 1 and 2 are used, T1 and T2 are equal. So T3 can only be greater than or equal to T1 or T2. So that is most important distinction between used versus unused. So pay close attention to this formulation. So this is the user equilibrium formulation based on those assumptions I just mentioned. So if there are n routes, remember we are not talking about links, n routes between any OD pair, each one like 1, 2, 3, 4, 4, 1, 2, 3, 4, 5, 6 to n, that many routes are there. So if you have each one of that route travel time is designated as t sub n, and volume on that particular link is xn, I'm sorry, not link, on that particular route is n, that volume being going from O to D. There are 100 trips going from O to D, and they are split among 4 routes. The total has to add up. So the total of that has to add up to that 100. So if you have Q equals 100, and then you have x1, x2, x3, and x4, there are 4 routes used. Sigma xn equals 100. So that is what this condition states. So in that particular state, if all 4 are used, the travel times t1, t2, t2, t3, and t4, they are going to be equal. So that is this mathematical formulation. So if you look at, let me pause here a second. So let's take a look at this formulation, mathematical formulation, for a second. It looks very intimidating. It actually is, but when you really take a closer look at it, it's not that intimidating at all. What you have here is a travel time function. Remember what we have, BPR function? BPR function is nothing but a travel time function of T sub 0, it's volume capacity ratio, right? So it's essentially, for each link you have a volume capacity ratio, a travel time relating to volume capacity ratio. If you can integrate between 0 volume to the maximum volume that link can take, which is what this term here states, then you sum it all up among all the routes in the all the individual link segments in the route, all the links that are used in any route. There are several different ways I am putting it. Then you have this with the subject to the condition, the total flow between O and D is going to be equal to the total number of trips if it is 100. So sigma of all the routes that are used is going to be 100. So let's take a look at this in a pictorial form. So let's take a look at this formulation in the context of a 2-link network. You have, let's say, this is your O and this is your D, and route 1, route 2, or link 1, link 2. Sometimes I may be using interchangeably, but route is the best way to keep in mind. So route, it may consist of a set of links. So if your travel time function for T, route 1 is, let's say, T, or the in play, whatever is in play, at any given time you have the volume W, and then this is going to be your T. So that is the function given, right? If you integrate it from 0 volume to here, actually this is, should read V1, not VA. So you are integrating between these two, so you are getting this area, and that's what this whole function is talking about. I mean, this formulation is talking about. And then if you will have similar thing for link 2 when you add them all up, and that sum is going to be minimized in this mathematical notation. So the best way to illustrate is to talk about a problem. So here is a problem that is taken from Mannering and Washburn in your CEIE 360 book, chapter 8. Forgot the actual problem number. But this problem states it's a two route network, route 1 and then route 2. So you have two routes, 4500 vehicles are going from point A to point B. So the origin is from origin to destination 4500 are going. Route 1 has 60 miles per hour and it is 6 miles long. Route 2 has a speed of 45 miles per hour and it is 3 miles long. So on route 1, for every 500 vehicles added on route 1, the travel time is increased by 2 minutes. On route 2, the travel time is increased by square of the number of vehicles. And we are required to find out equilibrium travel times. So just pause it here and then read the problem again, and it will be much clearer when we are solving the problem if you understand the problem first. So first and foremost, we need to find out what is your travel time function is. This is basically link performance function. So we need to formulate that. It is verbalized to us, but we need to put it in mathematical notation. First they said route 1 is 6 miles long and travels at 60 miles per hour. So what will be the free flow travel time? 6 miles, 60 miles per hour. So that will be essentially 1 mile per minute or 6 minutes. It will come to you. Just work it out. It will be much easier. 6 miles long, 60 miles per hour. So 1 minute per mile. So that's 6 minutes. So now the travel time. So the t sub 0 is 6. So this is t sub 0. And now this goes for every 500 vehicles up, it goes up by 2 minutes. We would like to normalize this for every 1000, let's say for every 1000 vehicles, for every 500 if it goes up by 2 minutes, for every 1000 we will go up by 4 minutes, right? If we find out this route 1, the volume on route 1 is x1, so x1 expressed in thousands of vehicles, then we will have 4 times x1. So free flow travel time plus as the volume increases it goes up by that factor. So this is the link performance function for route 1. What will it be for route 2? So for route 2 you have 45 miles per hour speed and then it's 3 miles long. So to get the free flow travel time, you will get it's 3 miles long for 45 miles per hour, and that many hours it will take times 60 minutes to an hour. So you will get 4 minutes free flow travel time. So t sub 0 for t2 free flow travel time is 4 minutes. And now travel time goes up by square of the volume. And if the volume on route 2 is going to be x2, so x2 expressed in thousands as in the previous case, we want to be expressing the volume in the same units, otherwise we'll have problems solving the problem. So x2 is expressed in thousands volumes, so it goes up by square of the volume, so it will be x2 square. So this is your travel time function on route 2. So let's take a look at this. We just came up with t1 is 6 plus 4x1, t2 is 4 plus x2 square. So now we have the total volume between point O and point D is 4,500 vehicles that was given to us. So remember, we are expressing both x1 and x2 in thousands of vehicles. So if you really formulate it in thousands of vehicles, that's how the formulation is going to look like, or x1 and x2 is 4.5. So we have three equations to work with and solve this problem. First and foremost, we want to find out is, will both routes be used or not? Well, you can clearly say they will be used. Just an intuition tells you that they will be used, but there is a mechanism to find out. What if we put all 4,500 vehicles on one route and then calculate the travel time, and on both cases, let's put x1 equals 4,500 and x2 is 0. If you put that one, if x1 is the only one that is used, the route 1 is the only one that is used, and route 2 travel time has to be higher than equal to or higher than route 1's. If you substitute like that, T1 will be 6 plus 4 times 4.5, so approximately 24, is it? So that's, yeah, it's 24 approximately. So that's T1. So in this case, T2 will be, while x2 is 0, T2 will be 4. So T2 is greater than, T1 is greater than T2. So it cannot be in equilibrium. This system cannot be in equilibrium, because at equilibrium T1 has to be T2, or at least T2 has to be higher. T2, which is not used, has to be higher than T1. So just by looking at this itself, you can say both routes are used. Another way to check it is also, this time you put x2 as 4,500, x2 as 4,500, and x1 as 0, and then solve this for T1 and T2, you will get similar answer. So there is no question, both routes are being used, and therefore the system has to be in equilibrium. We have to solve for it. For a two-link problem like this, the simplest solution is a graphical solution. So what I did here is I put it in a spreadsheet. I put volume on x1, route 1 volume only, and then I computed the travel time on route 2 and travel time on route 3 based on x1. So basically the x2 will be 4.5 minus this value, and I substitute that into our T1. Remember, we had T1 equals 6 plus 4x1 square, and T2 equals 4 plus x2 square. So x2 is nothing but 4.5 minus x1. So using that, I built this spreadsheet, and let me erase this so you will have a clear understanding again of this spreadsheet. Now look at the ones I highlighted in blue. As the travel time on route increases, travel time on route 2 is decreasing. There comes a point, there is somewhere in between 1.5 and 1.75, there is inflection. As it went from 12 to 13, this went from 13 to 11. So that is essentially where there is the equilibrium is struck. So if you plot route 1 volume, which is this red here, and route 2 volume with a absolute 4500 as your control volume, if you pay a little bit of attention, so I kind of reverse this. The curve actually, if you really plot it from left to right, it should look something like this, but I reversed it. I reversed that curve. So let me make it less shabby or less crowded so you will understand. Okay, now take a look at pay attention to the chart itself. Chart, you have, when these two curve meets, that means the travel times are equal. So approximately between 12 and 13, that's where you have. So this is equilibrium state when travel times are equal. And this, from left to right, the magnitude is x1. From here to here is magnitude is x2. I'm saying magnitude because you have to get 4.5 minus whatever the value here is. So this is your graphical solution. Fairly easy, right? Piece of cake. Now it's even easier to solve it algebraically. We have travel time 1 on route 1 equals travel time 2 at equilibrium, right? At equilibrium. So which means 6 plus 4x1 equals 4 plus x2 square, and we also have this conservation of flow. So total flow is going to be equal on both routes. So from this you can rewrite x1 in terms of x1 equals 4.5 minus x2. That comes from this condition. So if you substitute that value here, you got only x2 unknown, and solving for x2 you have 2.899. Because we are talking in thousands of vehicles, x2 value is 2899. And x1 is basically 4.5 minus x2, or 4500 minus x2, you get 1601. And if you substitute these values into T1 and T2 equations, you get exactly 12.4. So let's take another look at our graphical solution. So we got, by algebraically solving it, we got 12.4 approximately. So that's where we are. So this is around 12.4, and the volume we got is on x1 we got 1.669 something like that. So that's exactly where we are. So the graphical solution and your algebraic solution agree with each other. So the third way to solve this problem is using the mathematical programming techniques, using the same mathematical formulation we seen earlier. So we formulated this as an objective function subject to certain. Objective function is to minimize the sum of all the areas under the travel time function curve from 0 to the volume, from 0 volume to the volume at which the system will be in equilibrium, 0 to the volume where the system will be in equilibrium. And in that state, the sum of all the routes, the links in the routes, that area under the curve is going to be sum of the areas under the curve is going to be the minimum, absolute minimum. And that is the mathematical formulation, and that is what is based on Wardrop criteria. To illustrate this with our two route two link problem, OD you have 1 there and you have 2, and in route 1 you have the travel time function given by 6 plus 4W. We use W here because for integration, that's at any given point in time, the volume on that is indicated by W. And for route 2, this is it. And the integration is done between 0 and the volume on route 1, x1, and from 0 and volume on route 2, x2. So that is what we are integrating over. So that's what this objective function reduces to for this two route problem. And now we have the boundary, we have the conservation of flow, which is essentially x1 is 4.5 minus x2. And if you substitute 4.5 in minus x2 where it is x1, and this equation is written in this form. So I blurred out the first three steps here to follow up with the next steps. So we left here in the previous slide. So we substituted the value of x1 as 4.5 minus x2, and when you continue with your integration, that equation will take the form like that. Integration is continued, and then the upper and lower boundaries are 4.5 minus x2 and 0. Here the lower boundary is 0, upper boundary is x2, and that equation further transforms into a third order equation in x2. So we know this particular case at minimization, you have dsx by dsx2 will be 0. Thank goodness that brings down to a second order equation. You can use the quadratic formula to get root of the quadratic equation formula to obtain the value of x2. So which will be 2899, which is essentially what we got using algebraic formation or algebraic formula. So the travel time we used right now early in an earlier problem was like t1 equals 6 plus 4x1, right? So this is not a typical travel time formula, but in the earlier problems we solved in iterative problem or incremental, we used a BPR function, something like this. That's the travel time function, link performance function. And travel time on in this particular, this is a different example of similar nature, but the travel time is given as a BPR function. On route 1 you have 15 minutes, route 2 you have 20 minutes travel time, free flow travel time, and the volume on route 1 is V1, volume on route 2 is V2, capacities are 1000 and 3000, and total volume going from A to B is 8000. This is the problem, and solve for user equilibrium. So this is typically what we come up across in user equilibrium problem for traffic assignment. So first let's look at the graphical solution. Same way, use the travel time function in a spreadsheet. So approximately, I mean, you can do that on a graph, an engineer's graph paper. You can come up with the same solution. So when the volume changes on, actually this should read volume on route 1, volume on route 1. Volume changes from 2000 to 2250, You go from 51 to 72.67 here. Here is the inflection point somewhere there. So that brings me somewhere, if you look at the chart, you will see somewhere here is your equilibrium travel time. This is equilibrium travel time, ETT, equilibrium travel, user equilibrium travel time. And the volume, reading from left to right, somewhere between 2000 and 3000 is where you have route 1 equilibrium travel flow. And 8000 minus that will be route 2 equilibrium travel flow. Graphical solution, again, very straightforward, just like in the previous case. Only difference is the shape of the travel time curves is different. Let us see how to solve this user equilibrium problem where travel time is a BPR function. In other words, it's a volume capacity, it's a function of volume capacity ratio and the order to the order of 4, okay? So we know at equilibrium, T1 equals T2. We are assuming both routes are in play, and they are. Now, if you can do the same check, by the way, by putting all the volume in one route and then checking the travel times, you can still say, you can come up with a conclusion that both routes are in play. So there's no point in doing that again. So equating T1 to T2, we have this formula. And we also have conservation of flow. Total flow on route 1 and route 2 combined has to be equal to 8000, which is given, or volume on route 1 equals 8000 minus volume on route 2. That's what V1 equals 8000 minus V2 states. Substituting V1 value, we get this guy, this equation here. Now, pause a second and take a look at this equation. It's a function. If you reduce it, rearrange and reduce, what are you going to get? You're going to get a fourth order equation in V2, which is a function of V2. It's a function of V2. And at equilibrium, this is going to be, differentiating this is going to give you the lowest point, right? That's with the minimum. At equilibrium, this function value is going to be minimum. So you differentiate it and equate it to 0, you get a third order equation. Still, it is not the same as third order equation. It is not so difficult to solve it, especially if you have computer tools. But still, it's quite a difficult proposition compared to a second order equation where it's easily, you can use the quadratic formula, x equals minus b plus or minus square root of b square minus 4ac divided by 2a. But still, let's say if you solve it using, say, a spreadsheet or some other mechanism where you can get the third order roots, V2 you will get 5847. Okay. I'm just trying to make you understand or appreciate the complexity of this problem. It's not that you are required to, you will not be required to solve this kind of a problem. Earlier type of problems, yes, but not this one. You just have to pay attention still, because you have to appreciate the amount of work that goes into this equilibrium assignment. Now the third method, just like in the previous problem, you have the mathematical solution, same thing, T1, T2, and if you use your objective function, it looks something like this. Subject to the condition that T1 equals T2 and volume conservation of flow V1 plus V2 equals A3. These are the constraints, they call it, constraints and this is the objective function. Constraints and objective function. Now, pause for a second and see how you're going to solve this. Give it a shot in the homework and see if you can do it. And this is a challenge homework. Probably I might come up with extra credit for this one. This will be a challenge homework. But it can be done. By the way, this is not impossible to do, but this can be done. You will get ultimately the same solution as we got in algebraic way earlier. So net, whether you use the mathematical formulation or whether you use the algebraic solution or whether you use the graphical solution, at the end of this, the solution of this problem is going to be something like this. We started with the free flow travel time on link 1 as 15 and on link 2 as 20 minutes. By putting 8,000 vehicles going from A to B on these two links, so to reach the equilibrium travel time of 63 minutes on both links, you will have 2,153 vehicles on route 1, whereas 5,847 vehicles are coming on route 2. And that is the solution for this particular problem, which uses travel time function in the BPR travel time function. Now let's revisit some of the problems we have solved earlier using different methods. The same problem actually we solved using different methods. All or nothing, put everybody on this link and it said 136 minutes, and there's nothing here, nothing here. The incremental assignment used 23.8 here, 46.6 and 16. The travel times are not anywhere but equal. And now if you look at the iterative method without damping, you have that 15, 21, 16. They're better than the earlier two, but still they're off. But look at the iterative method with damping. They're not as bad. They're not as bad at all. 15.1. If it is equilibrium, everybody has to be equal, but they're closer than the other three. So if there is anything that comes a little bit closer to your equilibrium solution, is this thing, iterative with damping. That's why that method is still in use. So it's just a comparison of user equilibrium with other methods we have solved before. Let's get tough on this right now. Now we add one more route, just one more route to the problem. You have route 1, we solved this route 1 and route 2 earlier. Well, with difficulty, we solved, it was not a piece of cake, let's say, with some difficulty. And now there is a third guy in play, and all three will be used. Trust me, they will be used. So the third guy has 21-minute free flow travel time, and the function is something like that. The capacity is 1500 for this. Now do the same assignment, equilibrium assignment on this network. Now first let's look at graphical. Can we do this? Okay, yeah. Route 1, we know the previous way we can plot it, and route 2 we can plot that way. Where are you going to put route 3? How are you going to manipulate this chart to include route 3? It's not that easy. I mean, it's not possible. It is impossible. It is impossible to put that graphical solution. So the graphical solution for this case is out. Now let's look at algebraic solution. Algebraic solution, now you have T1, T2, T3. Well, they're all equal, so at least we give you that. There are total 6 unknowns, and 1, 2, 3, 4, 5 equations. So if you know the basics of simultaneous equations, number of unknowns minus 1, if you have that many equations, you can solve that problem. In this case, it's possible to solve it algebraically, but it's going to be a tremendous effort to solve it. We are not doing it, by the way. Breathe easy, we are not doing this. Now, the mathematical solution. Now, just remember, we just added one more route with a travel time function of this t3. And now, your objective function added one more element here subject to this conditions. What do we have to do now? Yes, it is complicated. Remember, it's only one more route added. It is the simplest problem. If going from 2 to 3 routes is going to make the problem so complicated, imagine how complicated solving this problem for network of Washington DC metro area. So it's mind-boggling. What would you feel like doing now? Yeah, give up is exactly what you would feel like doing, especially if you are given only a calculator and a piece of paper and a pen to solve this. Even a spreadsheet is not going to help you much. I'm talking about just a 3-route problem. Forget about Washington area network problem. So there is hope in this seemingly hopeless situation, and that comes in the form of Frank-Wolf decomposition. It is a heuristic which I will just show you the logic of it. So it's in one of the papers I gave, which you could have downloaded it. It is written by Chatterjee and Venigala. So it's a book chapter I wrote with Dr. Chatterjee, and in that there is this algorithm which is it's an iterative algorithm. Iterative meaning there are a number of iterations. This is a feedback loop for iterations. So we are not going to get into this details of this. This is actually a graduate level. We will be getting over this in a graduate level course, but not here. Using this is called a heuristic, meaning it gives you an approximation for your mathematical formulation. Remember, the basis for this one is the mathematical formulation. Minimize sigma of 0 to x. Remember that objective function formulation? That objective function formulation and those constraints are the ones that go into this heuristic, and it marvelously decomposes on a step-by-step basis and gives you an absolute minimum and a unique solution for travel time, user equilibrium travel times. That is what this heuristic does. Luckily, we are not covering that in this class. So the second method is system optimal. First one we talked about so far, user equilibrium. We spent so much time because that is the one that is used the most these days. System optimal is like it will utilize various routes such that the overall vehicle travel time means vehicle minutes. So number of vehicles times the amount of travel they do. So that's vehicle minutes. They will be minimized. So it's basically an area under the curve. This is mostly idealistic situation. Idealistic means like utopia. Well, it's basically saying you and I travel with the sole goal. You and I travel from point A to point B, which are totally independent of each other in such a way that entire system will, the travel time in the system will be minimized. That seems like a stretch, even though there is a theoretical proof and it is solvable using computers, but it is not practical. It is difficult to ever realize in practice, so it's not practical. But still, the scholars that we are, we will learn a little bit here. I may not have taught this in the class. I might have skipped this for you to go through on your own. So this is, pay attention to this in the video. So this is the system optimal formulation, and this is less intimidating than the user equilibrium formulation. So if you have whatever the maybe the curve, travel time curve is, and in the system optimal state, its travel time is, let's say, if it is link 1 T1 and its volume is x1, a product of these two is this, it's a multiplication of that, so that is what you are getting it, and you are minimizing the sum of that total travel time, vehicle minutes of travel time, you are minimizing the sum of that. So subject to the condition that conservation of the flow, total flow between origin and destination pair is going to be equal, and the flow has to be positive, 0 or positive. That means there should not be any negative flows at all. Okay, very simple. The objective function of the two links is volume multiplied by travel time of route 1, volume multiplied by travel time of route 2. So that will reduce to, in x1 and x2 terms, 6x1 plus 4x1 square plus 4x2 plus x2 square. And if you, x2 cube, sorry, this is x2 cube. We also know from conservation of flow, you have x1 equals 4.5 minus x2. Substituting and then reducing, you have everything in x2, a third order in x2, third order in x2. By differentiating with respect to x2 and equating it to 0, which is system optimal, at system optimal, that is the minimum, and you will get x2 value and x1 value as 2467 and 2033. So if you plot this system optimal solution, it will look like this. Remember, I am not, in this case, pay attention to this, I am not plotting this as a conservation of flow. Earlier I drew it at 4.5, right, in a user equilibrium solution. No, I am not doing that here. Also earlier I plotted this guy, route 2 from this side, so I am not also doing that right now. Rather, what I am doing is I am plotting everything from left to right. So this is route 1, this is route 2. Now, what does system optimal mean? System optimal means basically travel time or volume multiplied by the travel time. So in this case, let me draw a color so there won't be any confusion. Okay, let me draw this. For link 1, that is the T1 times x1. So this rectangular area, that's T1 times x1. So let me draw this for link 2 in a different color. So this purple here is T2 times x2. So these two sum is the absolute minimum possible. So that is the solution you got using that mathematical formulation. This is not a graphical solution, it's plotted and explained. the solution we got, I'm plotting and explain. Don't confuse this as your mathematical, um, graphical solution, not at all. So I hope you understand the sum of these two rectangles is what we have. Okay, pay no attention to this box here. I annotated something incorrectly there. Just don't pay any attention to it. So the system optimal problem is basically how does it differ? This solution, how does this system optimal solution differ from user equilibrium solution? So if your total travel time in the system, how you compute is x1 is the volume on link 1 times travel time on 1 plus x2 times t2. Okay, so that is your total travel time in the system. You can compute the same value for user equilibrium as well as system optimal. So if you compute that for user equilibrium, which we solved earlier, the user equilibrium travel time is 12.4 on both routes, and there are 4,500 vehicles. It doesn't matter which route they took because the travel time on both routes is 12.4. So when you convert that into vehicle hours, that will come to 930 vehicle hours. That is the total travel time in the system. Pay attention to that. Total travel time, vehicle hours of travel time in the system. Vehicle hours of travel time in the system. With the system optimal, we got travel time on route 1, which was computed. We haven't computed that yet, but substituting the the volume on route 1 as 2.033, you get travel time on route 1 is 14.13 and travel time on route 2 as 10.08. Now watch this, these are not in equilibrium, not in user equilibrium, because user equilibrium, this is not the user equilibrium definition. System optimal allows you to have different times for different routes. So note that down somewhere. System optimal allows competing routes to have different travel times. So that's basically something you should know. Okay, now continue with this. I just cleaned up the slate here. So earlier we had the system time is 930 vehicle hours in user equilibrium, and we computed travel time on route 1 to be 14 minutes, 10 minutes on route 2 for system optimal solution. Using the same formula, the system-wide vehicle hours traveled in system optimal case, this is the system optimal case, is 893. The system optimal, the very basic formulation is that this is going to be absolute minimum. You cannot have anything less than that in the system. In the user equilibrium case, you had 930 minus 893, and that is a difference of 36.8 vehicle hours. Remember, user equilibrium, users are maximizing their benefit. System optimal, users are maximizing users are maximizing their benefit, or you can also say users are minimizing their travel. In system optimal, users are being altruistic and they're trying to reduce or minimize the system-wide travel time. So that is why if this utopia can be achieved, you will have less fuel consumption, less emissions, etc., etc. It ain't going to happen. But that is the theory. So let us summarize. Equilibrium method is, whether it is system optimal or user equilibrium, both are theoretically sound. User equilibrium makes practical sense, but system optimal doesn't make any practical sense. And user equilibrium is the most used, so therefore, even if you don't understand the Frank-Wolf decomposition, which is the one that every computer program does, including your QRS2, but you just understand the complexity of the problem. That's all the purpose of this video is, to understand or have an appreciation for the complexity of the problem. So let's do a module summary. In module 6, we started with explaining the I/O for the traffic assignment, input output. So the first one that comes into it is zone to zone vehicle trip exchange matrix by time period. Same thing, time period specific network input, and you get time period specific network loaded network, that is as your output. So that's what we went over. Then we went over a pathfinding algorithm, which is essential for no matter which, including user equilibrium, you need a pathfinding algorithm. So you need to understand a methodical way of finding paths, which is what we learned. We call that label correcting algorithm. And we did an all or nothing assignment, even though all or nothing by itself nobody uses it, but all or nothing is a part and parcel of every other assignment, including equilibrium assignment. And we talked about stochastic assignment, which presumably makes a lot more sense, but it's almost impossible to practically implement that. And then we went over capacity restraint. As the volume increases, travel time increases by some function, and we introduced BPR function. And then that we called it link performance function, various names for that one. And using that capacity restraint, we talked about iterative method, where incremental method. Incremental method, we used 40%, 30%, 20%, and 10% in 4 iterations we assigned, each time updating the travel times on the links. And then we went over iterative method without damping first, and then with damping. And then we went over 2 equilibrium methods, user equilibrium method and a system optimal method. This being the winner as of today. User equilibrium is used everywhere or in most planning applications in the 4-step planning process. That pretty much concludes module 6, but I want to give you a little heads up on transit assignment. So the links of traffic assignment, they are not necessarily between what you call intersection links. They are different services running between stops and stations. So if you have a bus stop here and the next one is after several intersections, that will be one link. Between bus stops is one link. So just a conceptual difference. Again, I said it involves person trips, not vehicle trips. In highway assignment, it's vehicle trips. So it involves passengers, aka person trips. It's complex interchange patterns associated with passengers. In other words, you have walk, transfer, etc., etc. Those are the interchange patterns that are taken into consideration. So impedance function is not just travel time. It uses combination of travel, weight, and all kinds of timings, in vehicle, out of vehicle, etc. And then the fare structure is important. All you got to look at is utility function in mode choice modeling. So that forms a basis for impedance in transit network assignment. So some paths offer more than one parallel service. So in other words, you may have an express bus on the same route versus a local bus service. So these are some of the nuances that go into separately into transit assignment. And I think with that we conclude module 6. I hope you learned something in this module. Thanks for watching.